Hey everybody, by composite, I mean not prime. They're synonyms, I guess, or antonyms, not prime. And of course, a prime is defined to be the positive integers that are divisible only by 1 in themselves, such as 7, 11. Now, just to contrast this with another type of setup, what if n was prime? This is a very famous problem, Mersenne primes and so forth. But notice that here you get 7. Now, I'm not saying this is always true, but 3 is a prime number. 8 minus 1 is 7, which is prime. What's another one? Maybe 2 to the, let's just keep it easy, 2 to the 5th minus 1 is equal to 31. And so they're prime. Now, I'm not trying to say that this is always the case, but you can see why this problem here is of interest. We want to show that if n is a composite natural number, then 2 to the n minus 1 is also composite. And let's take a real quick look at what do we mean by composite. For example, 15 is composite since it's the product of two numbers that are between 1 and 15. Okay, 3 and 5 are both numbers or natural numbers between 1 and 15. And that's literally the definition of composite, which we will use right here. We'll suppose that n is composite, and everything's assumed to be positive integers here. So there's an r and s between 1 and n, just like 3 and 5 is between 1 and 15. So we get these two other integers, rs, such that, a little collision there with the s's and the t's. But so we write this, we replace n with what it's equal to, use laws of exponents to get to this point right here. Now, y'all, this part right here perhaps is the hardest part of the problem as far as just the basic algebra. If you think of all of this, if you have a to the n minus 1, you can think of this as 1 raised to the n if you want to, right? Okay, this is just equal to a minus 1. It's a little, at least it was for me. This is a minus 1 right here. A is just behaving like the 2 to the r in this case. And then you have a to the n minus 1. And this is just a fairly famous algebraic identity. A to the n minus 2. And the minus is, a lot of stuff cancels out. It's a lot of cancellation going on. Okay, and I'll do the ellipsis plus 1. Okay, and so it's slightly more complicated since n is written as the product of two integers, but this right here translates to what I have right here. But notice that this is guaranteed, this piece right here, since r will go back up to here, you know, our r is taken to be greater than 1. This part right here is greater than 1. Okay? And so that means this object here, which is the object we started with, has a factor greater than 1, so ergo it's composite. Okay, so QED. Okay, don't make me write it out. But again, all we did was use this factorization formula. Obviously, this factor here will also be greater than 1, which almost, you could make a mistake on this part right here, but you know that this part right here is guaranteed to be greater than 1, so we've proved that this is composite. But remember, that was what we were trying to do. I'll abbreviate, composite. Okay, so y'all, that's the end of the proof. And also, I would like to say this has an interesting, what they call contrapositive. You could also write this as if this is prime, okay, then this would have to be prime also. So in other words, we're starting out, well, let's just start right here. Suppose n is composite natural number. Show that 2 to the n minus 1 is also composite. Okay, but you could also say if 2 to the n minus 1 was prime, that would mean that n is prime. That would be what they call the contrapositive of this statement. So we've proved two things, and that might be more useful. If you run across one of these, something in this form that is prime, then assuredly n is prime because it is what they call the contrapositive to what we just proved. Okay, all right. That's all. Thanks for being.